Hello everyone, and welcome to another Competitive Programming 1 lesson. The topic today, topic 3, is going to be 2D array manipulation. So a little bit of review. A 2D array is an array of arrays. It's also sometimes called a matrix, and you can access individual elements with two indices, right? So array 2, 3 would access the element in row 2, column 3. That'd be this 2 right here. And you guys should be pretty familiar with 2D arrays already. They're a pretty simple data structure, right? If I asked you, for example, to iterate through the rows of an array in order like this, you should be able to do that, or iterate through columns. It shouldn't be too hard. But what we're gonna focus on in this lesson is going to be focusing on a little bit more interesting ways of accessing elements and iterating through arrays, or 2D arrays. So let's start off with the first example. Maximum neighbor. Given a 2D array of integers for a certain cell's neighbors, that is the cells directly up and down and left and right, which value is the greatest? So here we have a call to maximum neighbor, right, on this array, and index 1 for the row, index 1 for the column. So we see this, it would be this square right here. And what would be its maximum neighbor? Well, the one to its up, directly above it will have value 2. To the left will have value 4. To the right will have value 6. And to the bottom will have value 8. So the maximum out of all these four numbers is going to be 8. So we will have this function return 8 here. And if we think about how to solve this problem, it shouldn't be too bad, right? We could just check the adjacent cells by modifying the indices. So if we were given the indices RC for row column, we could just check the indices, or the array entries with indices R-1C, RC-1, RC+1, and R+1C. We also want to make sure that the cells that we check aren't out of bounds, right? So if we're right here, if we're given 0, 0, we don't really have a element in this matrix with column index -1, so we don't check this one. We should only check these two. So we need to add some sort of bounds checking. Alright, so just our basic way of writing this code would be something like this, right? So we have our input array and a row and a column index. We set our maximum number to the minimum value to ensure that we will always catch the actual minimum value. And so we start checking the bounds, right? So if row -1 is greater than or equal to 0, right? So if we go back, if row -1 here is greater than 0, so which means that it's within this matrix, then we just set max number to the max of the previous max number and the array entry. And we repeat this for the other three directions, right? So we check if our +1 is less than the array.length, right? So if this value, or sorry, if this element we're checking like down here, then this wouldn't exist. So again, we're just making sure that this is within the bounds. Then we just set the maximum number again to whatever this array value is, and so on and so on. However, we sort of see that this is a lot of code, right? Where it's basically the same thing repeated over and over again 4 different times, and it sort of seems inefficient. We could make this code actually a bit cleaner. We can create two sort of DRDC arrays, which means like a difference in row, difference in column arrays, with a change in row or column number for each direction. So if we think back to our original checking, we would have our original row column, and we just want to make sure each of these is within bounds. So we could just have a difference in row of -1 for up here, and a difference in column for 0 for corresponding to this cell. And similarly, we would have this difference in 1 for the row and difference in 0 for the cell, and you can see how this corresponds to each cell that we are checking. And now we can just simply loop through these DRDC arrays in order to have a cleaner code, like more condensed code, and not have to worry about 4 different pieces of logic in 4 different locations. So if we were to actually condense our code into DRDC arrays, we see that we just have bounds checking in one statement, right? So for each of these differences, -1, 1, 0, 0, and we loop through them, if the row plus the difference in the row is less than 0 and greater than or equal to 0 and less than the array length, and the column plus the difference in column is greater or equal to 0 and less than like the row length, then we just set it to the array entry, or the maximum number to the array entry again. So you can see how this can be also generalized to other ways of sort of checking the bounds of array entries, right? So we have a second problem here, hourglass sum. And an hourglass is simply a pattern of numbers in a matrix with this shape, right? So if we were given a matrix, then if the numbers in an hourglass would be in this shape. An hourglass sum is a sum of all numbers in an hourglass, and given a 2D array, what is the maximum hourglass sum in the array? Well, again, we can just iterate through all possible centers of hourglasses, right? So the center cannot have its center on the edge of an array, so we can just loop through all of these inner edges, right? Because if the center was here, then obviously we wouldn't have like the values here to create an hourglass. So we can use a DRDC trick to, instead of just looping like adding it manually, we could just use the DRDC trick to loop through all the values in an hourglass. And we can see how this happens here. So you can see here that we have our DRDC arrays. Here would be corresponding to the top of the hourglass, right? So if we call this position 0, 0, then this would be like -1, -1, -1, 0, -1, 1, etc., etc. And you can see how this sort of corresponds to each value in these arrays. And then we just simply loop through all of the middle array entries, right? So we start from 1 instead of 0, and we go to the array.length -1 instead of just array.length. And we do the same for the columns, right? So this ensures that we are only looping through the middle positions, right? These middle positions, and not touching these edges, because again, the center of this hourglass cannot be on the edge of the matrix. And then we just loop through the DRDC arrays, right, from 0 to 7, because there's 7 entries in here. We just add the array entry to the sum, and then update the max sum. If it's greater, then we update it. If it's not greater, then it just keeps max sum, and then at the end we return the max sum here. So you can sort of see how DRDC arrays can make sort of iterating through multiple positions relative to a single position a lot easier. Alright, so let's move on to the next question. Spiral matrix. So given a matrix, return the elements of that matrix in spiral order. So we would have an example here, right? If we were given this matrix right here, we would return it in spiral order. So we start at the upper left corner and go 1, 2, 3, 6, 9, 8, 7, 4, 5, right? You can see in this diagram, we're like sort of spiraling in, and then we return it in spiral order. So how might we accomplish this? Well, it turns out we can actually use DRDC arrays to sort of represent a direction that we're going in, right? So we can imagine the spiral as going in a certain direction until like it hits a like the edge of the matrix, or it hits a cell that it's already visited before, and then it turns clockwise. So if we think about, we initially start off going in to the right. So we start up in the upper left corner, and we initially imagine it going to the right. When it hits the edge of the array, we turn clockwise, right? And then we start going down. Then we hit the edge of the array, we turn clockwise, we go left. We hit the edge, go up, and then now we hit a value we've already visited before, right? We don't want to see this number twice, so we have to stop when we see this before, then turn clockwise, and then end here. So this can be accomplished by making DRDC arrays for each direction, then iterating through them, right? So for the right, we might say that difference in row would be 0, difference in column would be +1. Going down, we might say difference in row might be 1, and difference in column might be 0, etc., etc. We can also set up a visited Boolean 2D array to keep track of which squares we've accessed already so we don't repeat values, right? So if remember here, we already, like when we reach 4, we don't want to go up again because we've already seen 1. We've already included 1 in our spiral matrix. So we can just simply set up a Boolean array of the same size as our input array to keep track of which squares we've already visited so that we don't touch them again. And we finally stop the spiral when we have gone through all n times n values. And generally, for a matrix, we call the number of rows m and the number of columns n. So basically, when we've iterated through all the elements, we stop the loop and then return whatever we have, right? So once we have 9 elements in this array, 5 would be the 9th element, we would just return this final spiral order matrix. So let's take a look at how this might be coded. So we're just going, first off, we're going to assume rows is greater than 0, columns greater than 0. We're going to set up a new array list for like the spiral order. And we're going to just set the array.length is equal to rows and the first row's length to the number of columns. So we just use row and columns here, just variables for easier access, so we don't have to keep typing array.length or array index 0.length. And then we set up our Boolean visited array, right? So notice how Java automatically will set all these Boolean values to the default value, which will be false. If you're using C++ or Python, you need to make sure that you are actually filling in all these array values with the correct values, because I know for a fact that C++, for example, doesn't automatically fill in array like for a new array, it doesn't automatically fill in array entries with any default value. And finally, we would have our left, down, up, right, up, right? So if you think back here, we would first going, I guess it should be right, down, left, up here, but it's okay. We would have it go, each one is in order, right? So if we rotate clockwise, we would see it, it go from sort of moving this way to this way. And then if again iterating through next one, we would see move from this way to this way, and so on. And finally, we would set our current rows location, current columns location, and the direction we're going in. So the direction here would actually be the index of the DRDC arrays that we are going to be accessing. So again, we're initially going to be going 0, 1. So we're initially going to be going right. And then we're going to be incrementing this direction later when we turn clockwise. So for each value in the matrix, right? So we're going from 0 to rows times columns. So we're iterating through every single value in this matrix. We're going to first add our array entry, set the current array entry to visited, right? And then check to see if any of these are true, right? So if we hit like the left edge, or we hit the right edge, or we hit the top edge, or we hit the bottom edge, or the direction, or the array, sorry, the next entry that we're going to be accessing is already visited, right? So if any of these 5 conditions happen, then we should just change the direction, and then we should update the position. So thinking back here, right? So we start here. Our DRDC array is originally pointing right. So we have, we take this value, mark it as visited, go next. Add this value to the spiral order, go next. Add this value to the spiral order. Oh, we can't go next because we hit the edge. So we turn directions, turn down, right? So now, again, turn down, mark this, go next. mark this, go next. Oh, we can't go down here. And then you can see how this sort of eventually spirals its way to the center until we manage to get all the values in this array. And at the end, we're just going to return our spiral. Now, we're going to talk about one more way of iterating through a matrix. So here's an interesting pattern. The coordinates along a diagonal always sum up to the same values. So if we think about this matrix, right, here would be row 0, row 1, row 2, row 3, column 1, column 2, or sorry, column 0, column 1, column 2, column 3. And along a diagonal, right, each diagonal, we would have the indices sum up to the same values. So here we would have 0 plus 0 equals 0. Here we'd have 1 plus 0 equals 0 and 0 plus 1 equals 1. 2 plus 0 equals 0. 1 plus 1 equals 2. 0 plus 2 equals 2, and so on. So we can use this fact actually when iterating through a matrix diagonally. So the next example problem will just be diagonal traverse. Given a 2D array, return the elements of that matrix in a zigzagging diagonal order. So you can, again, assume we have this simple 3x3 matrix with 1, 2, 3, 4, 5, 6, 7, 8, 9. And iterating through in a zigzagging diagonal order, I've sort of added arrows here, right? So we start off this way, get the 1, then move down to the next diagonal, 2, 4, move up to the next diagonal, 7, 5, 3, move down, 6, 8, 9. Right, so you see here 1, 2, 4, 7, 5, 3, 6, 8, 9 would be the array that we would return at the end. So there's definitely like more than one strategy we can use here, but in order to demonstrate this sort of diagonal technique, we're just going to do the following. So we're going to iterate actually from diagonal 0 to diagonal m plus n minus 2, right? Because if you think about it, we would have m rows here. So the last one would have m rows here. So the last one would have index m minus 1. We would have had n columns. The last column would have index n minus 1. So the last diagonal here would just have, if we sum up the indices, we would have m minus 1 plus n minus 1, which would eventually simplify down to m plus n minus 2. So we iterate from diagonal 0, this diagonal, to diagonal m plus n minus 2, this diagonal. Then for each square in a diagonal, if it's in bounds, add it to the list, right? So we might start off over here, right, and then iterate through this way, through all the way through this diagonal. And then we don't want to, since there's no value here, we don't add it. We add this one, we add this one, we don't add one here. Imagine if like the diagonal sort of extended all the way across. And finally, we switch directions when you finish a diagonal. So again, here is another way. Here is the way we would write this in code, right? So we start off with an array list for the values that we're going to be adding. We have our rows and our columns, again, variables for easier access, so we just don't type the same thing over and over again. And finally, we have a direction, right? So 1 if it's moving from left to right, and -1 otherwise. You might also imagine how you could do this with a DRDC array, but we're just going to be doing something like this for now. So we're going to iterate from index 0 to, diagonal 0 to diagonal row plus column minus 2, right? M plus n minus 2. And having our start, if the direction is going to be 1, then we have our start at 0, start location at 0. Otherwise, we start at the opposite end. So, sort of to visualize this, right? So, we iterate from j equals start to the other way. And j here would be our column. So, if you think about it, we might have, if our column, right, if we're going in this direction, then we start at column 0, right? So if we're going in this direction, we start at column 0. We go and start here and then move up. We start here and then move up. So if this is just a ternary, right? If the direction we're moving from left to right, then we start at column 0. But if we're moving in the opposite direction, we're moving from right to left like this, we start instead at the column, right? So here we would have 0, 0, but here we would have 0, 1, right? Because this is diagonal 1, so we would start here and then go down. We would start here, diagonal 3, go down. So this is just a ternary operator that says if the direction is equal to 1, if we're moving from left to right, then we start at 0, else we go start at I, or the column number. Then we go from like the start value, right, wherever we start at, and go till we like lose our bounds, right? So either we go past the column, the last column, or our our column number goes below 0, and we add a direction, right? So if we're going up or right, we're going like this, we add 1. If we're going right to left, then we minus 1, and then we check if the index is in bounds, right? So if we have the column value is between 0 and columns, and the row value, we can just calculate the row value by taking the sum of the diagonal number minus the column number, right? So if we think back here, this would be diagonal 3. And then if we know that, for example, we are on column 2, then we can just calculate which row we're on by taking the diagonal number minus the column number. And that 3 minus 2 is equal to 1. So we know that if we know that we're on diagonal 3 and column 2, then we're going to be on row 1. So that's essentially what we're doing here. I minus j is just the row, right? So we're making sure that this row is between 0 and the number of rows. Then we're going to add our array entry, if it's within bounds, to our original diagonal order. And finally, at the end, when we finally finish iterating through this diagonal, then we're going to flip the direction, so we're going to be going in the opposite way. And at the end, we're just going to return the diagonal. So again, hopefully this makes sense, right? So we start, if we're going this way, then we start column 0 and iterate up 1. If it's going right to left, then we start at the column number, we start at 1, go down. Start at column 0, go up. Start at column 3, go down. Start at column 0, go up, and then that's the last diagonal. Alright, so we're going to end the lesson with another interesting way of looking at matrix or 2D arrays. So the Cantor pairing function is a constructive proof showing that the set of the natural numbers squared, and by extension the rational numbers, is a countable set. It assigns each value in the non-negative coordinate plane a number as shown in the diagram. So what it does is it goes along the diagonals, right? So the first diagonal we just have 1, the second diagonal we just go 2, 3, the next diagonal 4, 5, 6, diagonal 7, 8, 9, 10, and so on, right? So it's interesting because in this way we can basically assign every number on the coordinate plane a positive integer, which means that like z squared and z cubed and all that type of stuff, they're all countable sets. But the question here in this example is, given coordinates x, y, right, where x is the row number and y is the column number, what value does the Cantor pairing function assign it? Well, one way to look at this would just be looking at diagonals. If we know what diagonal we're on, we know exactly how many numbers came in the previous diagonals, right? So, for example, if we're on diagonal 3 right here, we know that there have been at least 1 plus 2 plus 3 previous numbers, right? So if we're already on this diagonal, the 7, 8, 9, 10 diagonal, we already know that there's 6 numbers before any number in this diagonal. And this works for any number, right? So if we're on diagonal x plus y, then the previous diagonals have used up the numbers 1, 2, 1, 2, 3, 4, all the way up to like this sum. So doing a bit of math, we get that this is x plus y times x plus y plus 1, all divided by 2 numbers, right? So again, here, if we're on diagonal 3, we know that they've used up 6 numbers because 3 times 4 divided by 2 is equal to 6. Then the current position can be found using the y-coordinate, right? So if we know that 6 numbers have been used up, then 7 here would just be 1 plus, or 0 plus 1 plus 6. 8 here would be 1 plus 1 plus 6. 9 here would be 2 plus 1 plus 6. And 10 here would be 3 plus 1 plus 6. So that means all we have to do is to calculate this, right? So this is an amount of numbers that have already appeared prior to it, plus the y-coordinate, and then add additional 1. And the code for it is very simple. Alright, so that would be the end of our lesson here, topic 3. Just as a review, we covered DRDC arrays today. We also covered sort of how we might use a DRDC array to sort of move a cell in move our current position in a certain direction, as well as how to use a visited array to keep track of which points we've already touched. And finally, we also talked about iterating through arrays in a diagonal fashion and how that could be used to solve some problems. The homework set should be on HackerRank, and it would be due, if I can find it, the homework set will be due on June 29th. If you have any questions about this lecture or about the homework, feel free to post on Piazza. We'll try to get back to you as soon as possible. Other than that, have a nice day and good luck.